So good morning, good afternoon, and good evening, everyone. Welcome you to this session. And may I invite all participants to turn on your cameras if you are able to do so. So let me introduce myself. I'm Jacqueline Lam from the University of Hong Kong. And I am one of the 2021 Healthy Longevity Young Catalyst awardees. This project was led by Professor Victor O.K. Lee, the project coordinator, and in collaboration with other international experts in neuroscience, including Professor Elena Gozes from the Tel Aviv University. And our project was sponsored by the Chinese University of Hong Kong and the University of Hong Kong. The title of our project is a directed graph neural network-based drug repurposing approach to identify a combination of drugs for the Alzheimer's disease, for the treatments of Alzheimer's disease. So let's get back to the topic today. Is our focus of this section. The focus of this section is basic and biomedical science, clinical medicine. So let me explain a little bit about the structure of this section. We have several Healthy Longevity Catalyst awardees from around the world who have volunteered to talk a bit about their innovation journey. I will turn to each of the volunteers today to introduce themselves, offer remarks for about 5 to 7 minutes, and then field any questions from others in this room. We truly hope this can be a dialogue and that others in attendance will ask questions or offer their own experience as they relate to the conversation. So even if you are not presenting today, we would like to hear from you. So let's now turn on to our speakers. The first speaker of today is Mohammed Alfatah. His project was sponsored by the Ministry of Health and National Research Foundation of Singapore. And the title of his project is Systematic Identification and Functional Analysis of Synergistic Small Molecule Combinations Targeting Aging. So let me now hand the floor to Mohammed to give the presentation. Mohammed, please.
Yeah, thank you very much, Professor Jacqueline, for your introduction. So, as I said, I'm just Mohammed Alfatah from Singapore. I'm Catalyst Awardee in 2021 from MOH in MRC, and I would like to talk about my the work what we are doing about the aging. So I would like to just share the slides. I would be very happy to if you share the slide. That's So can you see the slide?
Yes.
Yeah.
So the slide deck that Jessica Covington from NAM was sharing actually had your slides embedded as well as the other speakers. But happy to have you just show these, Mohammed, and then Jessica,
okay.
You can take over after.
Is okay?
Yep.
Continue. Okay, so thank you so much. And yeah, slide just changes overall. What we are doing in the lab is trying to identify the small molecules information that just decrease the aging and extend the health lifespan. So I will just introduce overall the work about the healthy longevity, what we are doing in Singapore in ASTAR lab. So as we all know that aging is the biggest risk factor for all chronic disease, including cancer, diabetes, neurological disorder, and also if you aged, you are more susceptible towards all the infection like the COVID. So the reason, because we know that as we age, our cells become dysfunctional and the loss of biology is decline, and that ultimately just decline the function of the cell, which is a fundamental unit of life. And that the aging biology is controlled and modulated by different environmental factors. You can see the lifestyle, food, nutrients, and if been genetic changes, for example, progeria, if you have mutation in a laminin protein, and the cellular aging is very fast, and the people very early looks like the age around more than 65 and 70, and more susceptible towards the chronic disease. So what we are trying to identify that can we stop the aging using the chemical or process, or we just by this way we identify the longevity medicine. So what we are trying to find the smaller molecules from natural product. We are also trying to identify the FDA approved drug for the repurposing, and we're also trying to find the biology and gene and protein associated with the aging that can prolong or just delay the aging. And we're also trying to find the combinatorial therapy approach, like the two drugs like rapamycin and metformin is one of the best anti-aging, is reported in a mouse model in a different across species. But the rapamycin is associated with, for example, immunosuppressive. You can use higher concentration that could be leads to immune less function, and that is a challenge for FDA approved drug. Actually, is maybe not it's very difficult to considering as an anti-aging compound. So that is a combinatorial therapy approach. So what we are using, the model system, and we are using one of the best model system, Saccharomyces cerevisiae. And as we all know, that Saccharomyces cerevisiae is the very simple eukaryotic organism, quite, their biology is quite homologous, quite similar to human, all metabolic process, and almost of the, like for example, autophagy is a discovered function in a yeast, and like rapamycin is a discovered in a yeast. So the biology is quite similar. And we are trying to identify the chronological lifespan, the targeting the chronological lifespan for increasing the health in human. So we can say that in chronological lifespan is quite mimicking to like neuron cells. When cells just divide, means they not divide, and but they had to be survive for a longer time. If the cell become dysfunctional, that will associate with the disease. So this is the yeast model, and we are using chronological model system. And if any compound which span is, then would be see the rapamycin is in our experiment, and see the supplementation of rapamycin cellular span of the yeast, and this is the proof of concept that our experiment is working. So we have screened more than 5,000 natural product and FDA approved drug, and we can see that more than 100 compound we have identified that increase the cellular lifespan, and some of the compound we have validated in a human cell line, and we can see that we have another approach that is there any FDA approved drug, any small molecules or natural product that could be also like nutrients could also accelerate the aging. And interestingly, we find that there's some of the FDA approved drug which is using for different treating for different diseases, and some natural product which is we commonly use that actually accelerate the aging. So we have to be very careful. Either we have to not use that one, or we have to find some alternative of things so that we can stop the or just stop the accelerated aging. And we also are trying to find the synergistic compound with the rapamycin, and we have used like 1 nanomolar, 2 nanomolar rapamycin concentration, which is not active in a yeast. Like you can see, like 1.2 and 2.5 is not is anti-aging concentration, but we got some of the compound which synergize. Like you can see the red all color here, and the green color is now is more active when you combine with some natural product or an FDA drug. So they're enhancing the rapamycin activity. So through this approach, we got two different combination. Like we got some of the anti-aging compound here, and here is a not anti-aging compound, but this actually compound actually accelerating, enhancing the rapamycin activity. Likewise, with 2 nanomolar, this compound is not the anti-aging compound, but they enhancing the rapamycin activity. And we have a four different combination that some compound which is not anti-aging, but they improve the rapamycin activity with low concentration and high concentration. Some of the compound which is working at low concentration but not high concentration. But quite interesting, we found that we have some anti-aging compound, but rapamycin worked antagonistically. Means this rapamycin, maybe at certain state, rapamycin is not the anti-aging, and it's quite interesting finding. We have now that at certain conditions, it could be possible that the rapamycin would be not the anti-aging. It could be that it could be the enhancer of the aging. So we are finding that situation, and it could be totally non-canonical finding. We will show that rapamycin could be not anti-aging at certain condition, but we need to validate in human cell line and in the mice model. This all result from the yeast model system. So we lab actually have a different resources and a platform. We providing the scanning platform for finding the anti-aging compound. We also trying to find the anti-aging compound which boost the AMPK, mitochondria, autophagy. These are all the actually suppressor of the aging. And we also have a research platform to find the molecules which inhibit the TORC1 activity, which is a aging regulator. And we have some of the compound which is already licensed for the patent, and we are welcome to go for the licensing for and as well as for development and commercialization for novel anti-aging compound or longevity compound with any collaborator who are interested or any companies. So with this, I would like to thank the Healthy Longevity Catalyst Award that helped to find the different different way to and support to do the aging research and help to connect different people across the world. Thank you so much.
Thank you, Mohammed. And may I now ask if there are any questions from the floor, from the audience? Okay, so I guess I have a question. If no one has a question right now in mind right now. So this is a very interesting project. May I know, or may you remind us again, what was the project especially innovative or novel?
So we have around we identify more than 100 compounds that has been not reported is anti-aging, like increase the cellular lifespan in the yeast, and yeast model system is very important and to find the aging biology. So that is the one we have resources and a novel thing. Second, new things that like we say that rapamycin is an anti-aging compound everywhere, is really well reported. But we identify, we found that rapamycin could be not anti-aging at certain state. And in a very recent paper in a Cell, even they also commented that rapamycin actually increased the mitochondria activity. Decrease the mitochondria activity, and mitochondria is really very important for inhibition of the mycobacterial tuberculosis. So it's very challenging. So that's why maybe we got a condition where maybe, I don't know what is the condition where TORC1 actually is required for lifespan. And so we have like different environmental condition possible. For example, maybe under certain different condition like nutrients, maybe you have a different condition where rapamycin is not the anti-aging. So we need to be very careful to go for like generalized use for the rapamycin. That's why we are also finding to some different anti-aging compounds. So there's two findings we have now, and we have also some synergistic compound and antagonistic compound for with the rapamycin. Yeah, that will be could utilize in the future. Yeah.
So thank you for sharing your novelties, and we wish your project every success.